neutral generalization of Riemannian manifolds with a lower sectional curvature bound. I'm going to give the definition. I'm pretty sure most of you know it, but just one definition. So we say an Alexandrov space, we define it as follows. It's of finite dimension and bigger than or equal to 1 is going to be a locally complete, locally compact, connected length space. This is with a lower curvature bound. Given in the triangle comparison sense. So I've omitted the case n equals 0. Those are not connected. They'll just be by convention 1 point or 2 points. Okay, so there's the definition we're starting out with. Okay, so what do I? So I'm supposed to click the recorded. Did somebody have a question?
No.
No. Okay, sorry, I thought I heard some kind of noise. Okay, so, again, probably most of you have seen this, but, what do we mean by triangle comparison sense? Just to review it. This means that we say the curvature of X is going to be bigger than or equal to kappa. And that's when, if I take any geodesic triangle, let's see if this kind of, nope. I have to do it in parts. My wobbly handwriting. Okay, so if I take a geodesic triangle, imagine the it's a real geodesic here, with side lengths set up as follows. This is in X. And then I look at the model space in 2 dimensions of constant curvature kappa. And then there we have a triangle, again, with the same side lengths. And comparison angles alpha tilde, beta tilde, and gamma tilde. And then the condition we impose is that alpha has to be bigger than or equal to alpha tilde, same for beta and for gamma. Okay, so this is just standard. Okay, so what else do we know? In an Alexandrov space, wow, this drawing on my iPad is not my forte, clearly. Here we go. So in an Alexandrov space, we talk about, we swap out the standard unit sphere in the tangent space of a Riemannian manifold with what we call the space of directions. And we denote it by sigma p. So we call this the space of directions. So they're the unit directions at p and x. It's the analog of the unit sphere in the tangent space in a Riemannian manifold. Okay, so what else do we know about the space of directions? It's going to be a compact Alexandrov space itself. And here, though, the lower curvature bound is 1. It's true for all p in my Alexandrov space. Okay, so the space of Alexandrov spaces properly contains the space of Riemannian manifolds with a lower sectional curvature bound. And there are 2 important results, classic results at this point, about Alexandrov spaces that make them especially appealing to study. The first is the theorem due to Gromov. And that tells us that if I define M, K, D of N to be the space of n-dimensional Riemannian manifolds, I want a lower curvature bound of K and an upper diameter bound of D. This space is pre-compact for this set in the Gromov-Hausdorff topology. Okay, so the second important theorem that we got for this is due to Grove and Peterson. And that says that if I've got a sequence of n manifolds, all of them with a uniform lower curvature bound, and I know that they converge in the Gromov-Hausdorff topology to an Alexandrov space X, then in particular, the curvature of X is also bounded below by this kappa. Okay, so the converse of this second result is false by work of Peterson, Wilhelm, and Zhu. Added an extra. So they found counterexamples of Alexandrov spaces. So they found Alexandrov spaces with curvature bounded below by kappa that are not obtained as non-collapsed Gromov-Hausdorff limits of manifolds with sectional curvature less than or equal to kappa. So a question we can ask at this point I suppose a reasonable question is, if we've got that the curvature of an Alexandrov space is bigger than or equal to kappa, is there some kappa tilde depending on this space? Maybe I should say, I'll leave it as it is. Although this should have been plural, but I fuss too much. Do I have some kappa tilde and a sequence of manifolds with their curvature bounded below by this kappa tilde, depending on X, that Gromov-Hausdorff converge to X? Okay, so it's worth noting that if I am given manifolds, so if I'm given a sequence of manifolds, and these manifolds are sitting inside of this class with a lower curvature bound and an upper diameter bound, and they all converge to some, I'm keeping the dimension the same, so it's a non-collapsing limit, then via the stability theorem, due to Perelman, I know that for sufficiently large I, I'm going to have that the maps from Mi to X are close to homeomorphisms. Okay, so what does that tell me? That tells me that the Gromov-Hausdorff limit of a sequence of non-collapsing Riemannian manifolds with a uniform lower curvature bound must be a topological manifold. Okay, on the other hand, Vitaly Karpovich showed that not all closed topological manifolds are indeed Gromov-Hausdorff limits of non-collapsed closed manifolds with a uniform lower curvature bound. So I want to say converse is false, and that's due to Karpovich. I'm going to talk a little bit, I'm going to put up his theorem in a second. Before I do, though, this leads us to the following definition, which has to do with the title of the talk. So I want to define what I mean by smoothability, because this is a good moment. So So we say that a closed Alexandrov space so I'm going to specify its lower curvature bound. We say that it's smoothable if it is the limit of a sequence of closed Riemannian manifolds with a uniform lower curvature bound. Okay, so specifically, there exists a sequence. So these are in M, kappa of N, but now I want this to denote the class of closed Riemannian manifolds here. So okay, so this is our definition of what we mean by smoothable. Okay, and Kopovich then showed that in particular, this is a really nice result. He characterized what the spaces of directions, that the spaces of directions all have to be smoothable as well. So the theorem states that if I've got a smoothable manifold, smoothable Alexandrov space, manifolds already are, then all of its spaces of directions are smoothable. And indeed, actually, they are the Gromov-Hausdorff limits of n-1 dimensional spheres with curvature bounded below by -1. So in particular, he gets that the spaces of directions have to be homeomorphic to n-1 spheres.
Excuse me, may I ask a question?
Yeah, absolutely.
Sorry, I'm a bit confused about the K, the definition of smoothable. Should that be the same K of the Alexandrov space, or could that be different? And I'm confused because now you...
Okay, it is the same K. So we're saying that this is the K. I mean, it's the exact same K in this case.
But
Well,
so
actually, no. You know what? I'm a liar because yeah, sorry. That's a good question. Let me make it, because I'm dealing with K prime. So yeah, it's a different K. Okay. It's K, so it's a K prime, and I just talked about that. Sorry, I'm like totally
I was trying to understand. Yeah, thanks a lot.
No, that's an excellent question, and I just mentioned this, that you don't always get them as limits, and in fact, that's what we show, is that you can't. I mean, well, not that you can't, but we're not able to construct sequences. Yeah, so the kappa prime may be somewhat lower than the kappa in particular. So yeah, excellent question. Thank you. Yeah, I forgot to put that, did not put the prime in my notes, so, and I should have. Okay, so yeah, there you go. Okay. Is there another question or?
Hello, can you hear me?
Okay, yeah, I think so, very faintly.
I must be a little confused. Does this mean that if Alexandrov space is smoothable, then it is so because from the Paramon's stability theorem, like so the are we saying that either X is a topological manifold or else the sequence that converges to it is collapsing?
So the stability theorem tells you that if it's non-collapsing, you know that the limit space is a topological manifold. In the collapsed case, we don't know that much.
Okay, so here we are mostly interested in the collapsing case?
No, I'm talking about the non-collapsing case. These are, this is in the definition, I'm saying here specifically that I've got a n-dimensional limit space and I start out with n-dimensional manifolds. So this is the non-collapsed case.
So in this case, X is a topological manifold?
Yes, absolutely.
Thank you.
Sure, sure. So then, an interesting result from this theorem, though, is of Kapovich is the following example. If you take the double suspension of the Poincare homology sphere, which I'm writing as, S3 modulo the binary icosahedral group, this is a topological manifold. And this is what I was mentioning prior to the definition. This is a topological manifold by work of Edwards. But it is definitely not smoothable by work of Kapovich. And that's because, in this double suspension, the suspension points, their spaces of directions will be suspensions of the Poincare homology sphere. So they are not homeomorphic to spheres in particular. They're not smoothable. Okay. So, is there a question? No, sorry. There was like some kind of weird effective noise. Okay, so at this point, a good question, according to me and my collaborators at least, to ask is, what other Alexandrov spaces are smoothable? Can we characterize when an Alexandrov space is smoothable? And we don't have an answer to that question, but I do want to mention recent work of Dyatlov that inspired our work. So there's a theorem due to Dyatlov that came out a little while ago. And it's specifically for quotient spaces. So if I let G be S1 or SP of 1, and I'm letting it act isometrically, effectively, and semi-freely. So I'm going to explain what semi-freely means in a second. It's not that common a term, although maybe all know it. Further, he specifically, in this theorem, his goal was to smooth a class of quotient spaces in the hopes of finding a new example of positive curvature. He didn't achieve the last goal, but he did show that you can smooth a specific class of quotient spaces. So in his result, he assumes as well that he's got the sectional curvature of two planes bounded, uniformly bounded from below, uniformly positive, bound on the sectional curvature of all two planes, sigma, that are orthogonal to the orbits. And you can do this in general for just a lower curvature bound too. So if you just pick a closed manifold, that's going to be good enough. And he supposes further, because of the way the smoothing is done, you need to suppose further that for all components, connected components in the fixed point set of the manifold with respect to the group action. So fixed point sets of the entire group, he's assuming that the codimension of these fixed point sets is equal to 2 times 1 plus the dimension of the group. Okay, then in this case, you can conclude that the quotient space is smoothable, and he wants it to be smoothable by positively curved manifolds. Okay, so I promised a definition of semi-free. Is this language, it's a holdover, I guess, from the 60s. So semi-free, what does it mean? This just means it's super restrictive. It means that G sub x, which is the isotropy group at x, so it's the group elements that fix that point. In this case, it's either trivial, it's either the identity, or it's the whole group. So specifically, if I'm looking at S1, for example, then that condition here on the components of the fixed point set translates to having all codimension for fixed point sets. And it means that the action on the normal 3 sphere is going to be precisely the Hopf action, because I'm saying that all of the isotropy groups are trivial or the whole group, and that's going to force it to be a free action on its normal space, in particular on its normal sphere. Likewise for SP of 1, that means that you're looking at codimension 8, so you're looking at again, the Hopf action literally on the unit normal sphere to the space of directions. Well, the unit normal sphere, sorry, to the fixed point set of the SP of 1 action. Okay, so this is very specific. It's just 2 groups we're looking at, but we instead, we've generalized this result to a broader class of quotient spaces. And so I'm going to write up the theorem. This is one of the few times I get to put my name first. So we're now looking at group actions. So we're only looking at compactly groups. But now we, there's a broader class of Lie groups that can act. So I want it to act again isometrically, well, and effectively, that's all, on a Riemannian manifold. Sorry, I want it to be closed. Okay. Moreover, so now we're going to let X be equal to the Alexandrov space we obtained from that is the quotient space. And we're going to suppose, this is where all the conditions come in. We're making assumptions now on the spaces of directions. So we're going to suppose that each space of directions is isometric to an iterated join of constant curvature. Spheres, and by spheres here, I am including spheres of dimension 1. So I want to include circles in here. We want to include circles here. Okay, so iterated joins of spheres are spheres, and we're just looking at constant curvature, bigger than or equal to 1 in general. Then the result we get is that X is homeomorphic. Basically, we get at this point that it's smoothable, but we have some specific conditions we can place on the smoothing. So it's homeomorphic to a smooth manifold M prime. Furthermore, if the curvature of M prime is bigger than or equal to kappa, then that implies that we've got a sequence of metrics so these are smooth Riemannian metrics. This is going to be ginormous. With sectional curvature of M prime, with each of these metrics being bigger than or equal to kappa minus 1 over M, so close to the kappa of the limit space. That converge to X. And Gromov-Hausdorff topology. Okay, so again, spheres here include spheres of dimension 1. So we're including spheres, circles of yeah, if you like curvature bigger than or equal to 1. If, I mean, and that's actually, you know, like, I should say, quote unquote, it's curvature in a different sense, right? Okay, so in order to, definitely don't have time to even get close to proving all of this, I wanted to make some comments about the proof, some general comments, and give an idea of how we do it in one of the easier cases, or at least what the basic principles of the proof are. So to start off, I want to talk about the structure of the orbit space, because that's very restricted. Dyatlev's is certainly extremely restricted. This is still very, very restrictive, but a little bit more general. So here we go. So I want to talk about the structure of the orbit space. And then I'm going to talk about smoothing and around isolated singularity if there's time. Well, hopefully there should be. Okay, so I just want to recall, or tell you for the first time if it is. If I'm looking at a quotient space of an isometric action on a Riemannian manifold, if I let pi be the projection onto the Alexandrov space, and I take p bar equal to the image of a point P and of the orbit of P then too, then the space of directions at P bar in X, excuse me, is by definition equal to the quotient by the isotropy group at P of the unit normal sphere to the orbit. Okay, so this is where SP perp is the unit normal sphere in the unit sphere of the tangent space of M. And this is the space, you know, it's the, yeah, it's the normal sphere to the orbit. Okay, so at this point, as I've said, you know, well, basically the restriction on the spaces of directions that we have from the theorem. So the theorem is saying they have to be, again, iterated joins of, oops, I don't want to do that, highlight it. They're iterated joins of constant curvature spheres. This places actually quite severe restrictions on the isotropy groups of the action. I want to recall a classification result of both Bredon in the smooth case and Gromol and Grove in the isometric case. So combining the two of them, together, we have some restrictions on what G is. So if we have G as a compact Lie group, acting isometrically, and effectively on the unit sphere. Okay, and then if this quotient is a round sphere, so a sphere of constant curvature, then the following are true. First, the G action has to be free. So this is really strong. G has to be one of these three groups. So it's either a cyclic group, a circle, or SP of 1. And then respectively, the dimensions of the spheres it can act on are 1, 3, and 7. And further, when G is connected, the action is then isometrically equivalent to the Hopf action. Okay. So these actions are going to impose, this result imposes constraints on the isotropy groups and hence on the G action on M itself. I want to describe some of the restrictions because they're important for the smoothing. But first, I want to establish some notation, and then I'm going to give a a really trivial example that hopefully illustrates what's going on with the notation. So, okay, so just recall that, when we're looking at a group action on a manifold, we get a stratification of M into smooth submanifolds by orbit type. I'm going to let S be equal to a stratum at a point X and M, and this is the union of all orbits. With isotropy conjugate to the isotropy at X. Okay, the strata are partially ordered by inclusion. We're only dealing with singular strata. I mean, you can divide, the stratification is going to be via principal orbits, those with principal isotropy. And then you can talk about all the singular strata. Here we have no exceptional, well, yeah, we don't have exceptional orbits. So we're just talking about singular strata, if you like. And I guess I'm going to try and denote with this curly S. This is going to be the set of all singular. Well, I don't actually use this. Well, no, I do. Set of all singular strata. Maybe I do. And then I talk about M reg, and that's going to be the set of all principal orbits. So that's M minus this, all the singular strata. I also want to point out that we do give a name to inclusion, to relationships between strata. So if I've got S, a strata that's contained in another strata, S1, and I don't have any other intermediate strata, then we say that S1 is a parent. That's horribly written. Of S. And then, if it's higher up than that, we talk about ancestors. Okay, so I wanted to give an example that is not really in the class of manifolds I'm talking about. I'm just going to look at G, because I want to give an example where I've got 3 parents. So I'm having this act just on Euclidean spaces. And unlike, in the examples, I'm, in what belongs to properly to the class of spaces I'm looking at for this theorem, this will be a quotient space with boundary. We don't have boundary in our cases. So the lowest dimensional strata though here is the fixed point set of the group action, and that's going to be the origin. And then I have 3 parents that are the fixed point sets of respective pairs of these guys. Well, actually, there are more strata, but I just want to do these guys, I guess. Because this is enough to write out. So you can, continue with this exercise and see that you'll get parents of these parents, or you get grandparents or ancestors, if you like. That will be products of these guys, but I'm just going to draw these guys. Basically, what's going to happen then is I've got M, and I'm just drawing to the N1, N2, and N3. So there'll be strata in between here. So I'm just going to do that like that. But these all go down to S. And in my quotient space, in this example, in the quotient space M mod G, this is going to be R3 So it's going to be this octant, the positive octant in R3. And if you like, this is the image of N1 mod G. The origin here is S. So we use different colors. This is N2 mod G. And this is N3 mod G here. If I go back to this regular, these, what I'm flashing here, so the planes then are also fixed by other elements. And yeah, so you can kind of see, this goes to what I want to talk about right now, is that if you look at the structure of the normal space to this strata, so this fixed point set in the original manifold, and then look at it in the quotient space, you can see it breaks off into the normal space. You can rewrite it as a Whitney sum in this particular case of the normal spaces of the strata restricted to each of its parents. And that's a general condition that we see happening in all of our cases. Okay, so let me just say that. Okay, so what we do, the group action then forces the normal space to a stratum, as I said, to decompose as actually a G-invariant Whitney sum of the normal space of the sphere, I'm sorry, of the stratum S in each of its parents. So what we get is a G-invariant decomposition of the normal space of S, the strata, and this persists then to the quotient space. So n sitting inside of it, these are n that are, by this I mean in the parents of S, and we can rewrite it as this. Okay, and what we get in addition is that each isotropy group, well, the isotropy group at X acts on each of the corresponding unit spheres sitting inside of these normal spaces in the parents, and this is a principal action. And if you let K sub X be equal to the kernel of the G action, the G sub X action, I should say, then GX mod K sub X is going to be one of these groups that I specified in the previous result. That's due to Bourdon and Gramal and Grove. And further, this is going to be free. Okay. So we get this structure. In the more general case, I don't really have time. I'm supposed to end at 45, I understand. So I want to give an idea really quickly of how we do the local smoothing in the isolated singularity case. So I'm just going to discuss the case of, I have a single isolated orbit, and one isolated singular orbit. The idea when you have a full, just a single strata is essentially the same. There's not much, not much happens different in that case. So to start, so I want to do, this is smoothing, I should say local smoothing. Yeah, so I want to do talk about local smoothing in the isolated singularity case. Okay, so just want to recall a few facts. We know that small neighborhoods of points in my Alexandrov space are almost isometric to the spherical cone over the space of directions. So I'm going to write that C of sigma P. So at that point, it suffices to smooth a neighborhood of the cone point in the cone over the space of directions. So basically, we want to find a sequence of smoother Riemannian metrics that Gromov-Hausdorff converge to our original metric. So at this stage, all we're interested in having, at the moment, all we're worried about is having some lower curvature bound. We adjust it later to make it the desired one with a conformal change. So I'm just going to ignore the whole question of doing the kappa minus 1 over m case. The simplest case to begin with is that where, as I said, we just have a single strata and it's isolated. So I'm starting out with this case where the sigma p is just Sn minus 1 of rho. And in this case, rho is less than 1. There are no quotients of unit round spheres that get you a round sphere of constant curvature 1. Okay, so instead of working with the spherical cone over this space, we actually work with the spherical suspension of the sphere that contains it, the constant curvature rho sphere that, well, constant curvature 1 over rho squared, I guess, sphere that contains it. So, oops. So we consider at this point the spherical suspension of Sn of rho. And I have some drawings to make this a little bit faster. So I have to scroll forward. Sorry about this. So I'll rewrite some of this. I just have to find them. Okay, here we go. This is the picture I want. So we're looking, I'll rewrite that. You consider the spherical suspension. And the point is here is that the cone of the space of directions is contained in the suspension of Sn minus 1 of rho, which is suspension. Oh, sorry, I meant to write, well, that's equal to the suspension of the space of directions. I should have swapped those inclusions. And this is actually contained in the suspension of this larger sphere that I want to look at. Basically, because it makes it a little bit easier to deal with. So here's the picture you want to think about. So this is, this is supposed to be my Sn of rho here, and then we've suspended it. These are my suspension points. And then within the Sn of rho, I've got these 2 points are supposed to pictorially represent. So I'm doing everything in low dimensions so I can draw it. These are supposed to be the Sn minus 1 of rho. And then when we suspend that, we're getting all of this over here. Okay, so we further want to actually, so we want to take advantage of the work of Green and Wu on strictly concave functions in positive curvature in geodesically convex spaces. So to do that, we're going to consider then, so we want to consider the hemisphere. So that's Hn of rho sitting inside of Sn of rho. So I'm just looking at the hemisphere then over here, and I'm going to suspend that. I'm going to let, I'm going to, well, yeah, so I'm going to let in the picture below that I'll put up, I'm going to let C be its center because that's relevant. And the boundary then of this hemisphere is actually my Sn of rho. So when I suspend everything then, so the suspension of Sn minus 1 of rho, which is my space of directions, that is the boundary now of something that's convex, which is this Hn of rho and a positive curvature. Okay, so this is the picture now I want to focus on. So I'm in this again, this is my Sn of, well, this is the hemisphere now. So that's Hn of rho sitting inside of Sn of rho. And I want to note here that, well, actually this gamma is going to be just a geodesic now from one of the suspension points, the top suspension point to C pi over 2. Okay, so this is the C that is the center of this Hn of rho. And the point here now is that the distance function from this boundary now it is concave down. It's actually strictly concave down as long as I'm not going along a geodesic. But it's also not smooth along here because this is a sphere of radius rho less than 1. So the angles here mean that if I'm going along here and measuring the distance, so that any point I'll be able to find shorter curves. So this is not going to be, the distance function won't be smooth there. So this is where what we do is we apply we use a transnormal adjustment. I don't know how to this distance function. Did I write it down? No. So we apply. So I'm going to apply the transnormal adjustment to the distance function from the suspension of Sn minus 1 of rho. This is my boundary. To make sure that it's actually strictly concave down. So the transnormal adjustment is just throw in a function, a real valued function that's concave down and strictly increasing. And that means I'm going to have f, which is going to be lambda composed with, oops, it's got to be the distance function. Okay, so now again, this is it's now strictly concave down, this transnormal adjustment, and that allows me now to use the work of Green and Wu to smooth this distance function. So that is, I can approximate it by a smooth function. From here, what we're going to do is we construct. Well, it's too far down. From here, what we're going to do is we construct these hypersurfaces. Oh, I'm way over time. Yeah, so, well, the idea is that we construct these hypersurfaces. They're going to be close to, they approximate level sets of the distance function. And we smooth those. We can show that they're diffeomorphic to spheres. And from there, at that point, then with these guys, you're going to split them in half. And you restricting the metric to each one of those. We got a metric approximation of the cone over the space of directions, which is what we wanted to do. So I guess I'll end there because I'm over time. I'm really sorry about that. I thought I actually had too little to talk about. So yeah, that's it then. Thanks very much for your attention. Sorry about going over time.